Dear students, welcome to our class on stability factor F. Stability factor F and Richardson number. I request you to subscribe to my channel Agrometeorology, Farmers and Rural Development, where in the earlier lectures we have already discussed elaborately about Richardson number. Before that, Richardson number, as I don't want to repeat once again, but academic interest to understand in this class, Richardson number or capital or small I is a dimensionless parameter which is extensively used in turbulence calculation in innumerable fields. Whether it is fluid dynamics, what not, I don't want to say repeatedly. I had already given the Richardson number. However, as far as agricultural meteorology is concerned, it has got wonderful applications, Richardson number. That's why Reynolds number and Richardson number, along with other non-dimensional groups, Nusselt number, Sherwood, all these things we have already discussed several. In future, we are going to discuss. Now, in this class, a small relation between this stability factor F and Richardson number, capital or small I, not Reynolds number, Richardson number. Richardson number is a typical dimensionless parameter used in the stability. How a stability can be applied. Now here, non-neutral conditions. There are three conditions that we discussed in the earlier classes. Number one, neutral conditions. Just during a overcast day, just before sunrise, just after sunset, and then the dawn. Entering. So these are the conditions where we expect a neutral, but non-neutral conditions means stable and unstable. Stable during the night time, surface is cooler than the above the ground surface. So air. During the daytime, surface is warmer than the air. So where we get more of unstable. Here, if you see the relation, very interesting. If you see the relation, Reynolds number 10 plus 10 to minus 10. Once again, Reynolds number plus 10 to minus 10. Now, if you take stability parameter, stability factor otherwise, it is the 0 here, 0, 0.5, 0.25, 0.125. Now, see, if you see the unstable and stable, here I have given very good, this appealing like, for you to, this is the stable. Under which conditions it is stable, under which conditions it is unstable as far as atmosphere is concerned. Now, when there is a free convection around minus 10 of Reynolds number, which is unusual, most likely the Reynolds number range between plus 10 to 0.1. Plus 10 to 0.1 is most common, that is the stable. Very unstable, minus 10. Now, under the unstable conditions, free convection, mixed convection goes on. Here, fully forced convection occurs where the stability factor F becomes unity. Stability factor becomes unity here, then 2, 4, 8. So, when stability factor becomes unity and Reynolds number becomes 0.001 almost. At this stage there is a fully forced convection, of course, then a damper force convection and no convection. Where there is no convection exists where Richardson number is close to 10. Virtually there is no movement of the air. So how we can interpret this one? Just for my academic interest and then for your knowledge, please understand this line. I would like to tell, when Richardson number is less than 1, when Richardson number is less than 1, free convection dominates. When it is less than 1, free convection dominates. Less than 1 minus. Free convection dominates. For values close to 0 here, for values close to 0, from here if you take plus, for values close to 0, F is closer to unity. For values almost 0 of the Richardson number, where F is equal to unity, stability factor is unity. F is closer to unity and fully forced convection dominates. Fully forced convection dominates. Then when Ri approaches 0.2 or greater, stability damps turbulence completely. Now see, this is what I would like to say, the relation between the stability factor F and the Richardson number Ri. Thanking you for your question.